Alright, so today we're looking at factor group. So I'm going to use an example to start with first, give you an idea and also give you some revision. So I'm going to start with a group where we are more familiar with. Let's say I got a group Z6 addition modulo 6. Right? So Z6 consists of 6 numbers 0, 1, 2, 3, 4, 5. Addition modulo 6. Now, let's consider a subgroup of Z6. Okay, we have more or less known last time that this is a subgroup. H consists of 0, 2, 4. So this is a subgroup of G. Let's call this G here. Subgroup of G. Then from this subgroup, we can construct left coset. Now, since the group operation is addition, I can do addition. So for example, what can I do? I can say 0 plus h. I still get back h again. I can also do 1 plus h. Everything inside h add 1 on the left. So that 1 plus 0 is 1. 1 plus 2 is 3. 1 plus 4 is 5. Now, any more different coset? If you try to say, I want to find 2 plus h, you'll find that you repeat the coset again. 1 plus h equal to 3 plus h equal to 5 plus h. 0 plus h is the same as 2 plus h equal to 4 plus h. So just repeating. So there are only 2 distinct cosets. Now, this number 2 here, if you recall what I say about this number 2 can we tell without calculation? Yes, last week we learned a little bit there. This can be calculated by taking the group, the size of G over the size of H. Where the size of G is 6, the size of H is 3, so you have only 2. That's why you can have 2 distinct cosets. And what would you call this number 2 here? This number 2 is called what? Index of H in G. Just a little bit of revision. We have this covered last week. Now, let's look at the Cayley table of this group. Right? I'm going to start fresh and look at Cayley table of this group. So far, all right? So far, the information I presented here. Okay, this is what we call a left coset of subgroup. Okay, now I'm going to construct a Cayley table for Z6 now. I'm going to insert a new page. Alright, so Cayley table of Z6. Addition modulo 6. And I'm going to use it this way. I'm going to put 0, 2, 4, and then 1, 3, 5. So the table will look like this: 0, 2, 4, 1, 3, 5. Alright? So purposely put the table like this. So addition modulo 6. So make a table. And then you fill out a table. So, for example, I just fill out a table. 0 plus 0 is 0, 0 plus 2 is 2, 0 plus 4 is 4, right? They are the same. 2 plus 0 is 2, 4 plus 0 is 4, the same. 2 plus 2 is 4, 2 plus 6 is 0 now. 2 plus 4 is 0 now. 2 plus 1 is 3, 2 plus 3 is 5, 2 plus 5 is 1 modulo 6. Alright? 4 plus 2 is 0, 4 plus 4 is 8, modulo 6 is 2, then 4 plus 1 is 5, 4 plus 3 is 1, 4 plus 5 is 9, modulo 6 is 3. So you can fill out the table. So this is 1, 3, 5, 3, 5, 1, 5, 1, 3, and then this is 2, 4, 0, and then 4, 0, 2, and then 0, 2, 4, right? So you got a table like this. So this is a table for Z6. The only thing is I rearrange the row and column. I put 0, 2, 4 together and 1, 3, 5 together. Now why I want to do this? Notice that 0, 3, 0, 2, 4 is actually one of the coset. 0, 2, 4 is one of the coset. Right? You say that this all together, all 0, 2, 4, right? This one also all 0, 2, 4. Okay, so we know that h, which is 0 plus h, is 0, 2, 4. And another one we have come across is 1 plus h is 1, 3, 5. So let me color them. So all the 1, 3, 5 are here. And basically you see that I just need 2 colors to color them. Now you compare a mapping. I want to use this mapping because I only use 2 colors only. Right? I want to compare this to a group table also have same 2 colors will do. Addition, modulo 2. Okay? 0, 1, 0, 1. Compare this group table. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. Okay? Now, I want to construct a homomorphism from Z6 to Z2. Okay, I want to do a mapping so that they have the same color. Okay? So what I'm going to do now is whatever element in Z6, I just take whatever number you have, modulo 2. Okay? Whatever number 0, 1, 2, 3, 4, 5, I just send to the same number modulo 2. Okay? So what does it mean? Based on that, image of 0 is what? 0. Image of 1, 1. Image of 2, 0 again. Image of 3, 1. 3 modulo 2 is 1, right? Image of 4, 4 modulo 2 is 0. Image of 5, 5 modulo 2 is what? 1. So I'm using this method, I find that 0 goes to 0, 2 goes to 0, 4 goes to 0. So you look at the yellow part, this portion. Okay, I'm going to highlight fully for you to see this portion. 0 goes to 0, 2 goes to 0, 4 goes to 0, right? So all these number goes to 0. Correct? So all this number goes to 0. All this number goes to 0. You'll find that, okay, this portion all goes to 0. 0, 2, 4 all goes to 0. 0, 2, 4 all goes to 0. And the one in the block, whatever number is, it all goes to 0. Right? Then you look at the right corner, right bottom corner, the block 2, 4, 0, 4, 0, 2, 0, 2, 4. What did it go to? Yeah, I just tell you 0 goes to 0, 2 goes to 0, 4 goes to 0. So the mapping will map all this block. Okay, the mapping will map this block all goes to 0. This block here all goes to 0. Alright? Now you look at the green one. All the 1 goes to 1, 3 also goes to 1, 5 also goes to 1. Okay? So all the green box here, this portion, all goes to 1. And then this portion here on the left, all goes to 1. So notice that these two tables, although they are different size, right? Although they are different size, they have the same structure. The color just match. If you ignore the number 135, if you ignore number 240, they all have the same color. Okay? So if you color 135 or green, color 024 or yellow, then you find that you get the table on the right side. Exactly the same. Right? Of course, you need not to color this way, but because if you say that, oh, left hand side actually got 6 numbers, you can use one color for one number. Of course, you'll get 6 different colors on the left hand side. But because I say 135, I'm going to color green, 024 color yellow, then get a table exactly on this. So when you have this happen, what does it mean? It means that this is a homomorphism. Right? So this means that this mapping here is a homomorphism. Okay? Remember what is the meaning of homomorphism? If a group is under addition, image of x plus y will be image of x plus image of y. This is a property of homomorphism. Okay? Then if this is a homomorphism, we can also talk about what? Kernel. Right? Kernel of this homomorphism is what? Is which number that goes to 0. Right? So this is the inverse image of 0. Which number goes to 0? We know is 0 to 4. Right? So this is a brief recap of what we mentioned last week. Homomorphism, kernel, and how do you tell the homomorphisms? One way is looking at and coloring them. Okay? Instead of testing image of x plus y equal image of x plus image of y, you can do this color scheme. Okay? Purposely arranged this way, you can find that. Alright, this is a homomorphism now. The kernel is 0 to 4. Right? And 0 to 4 happen to be a subgroup. Right?